Hello everyone, welcome to IMSC A82 Network Flow and Graph Theory for Spring 2023. Today's our lecture module is the Python tutorial for lecture 7. I'm going to ask you to download the several notebook. I will post it here after lecture and the lecture video. Follow out my lecture video and doing this, okay? The first model I want to introduce is solving minimal cost flow problems using capacity scaling, which is the successive shortest path method we mentioned in the lectures. In the lecture, we'll give you an example, walk you through step by step. But here is the version I found in the Network X and how to solve that. And in the Network X, the algorithm is called capacity scaling and actually is the successive shortest path problem algorithm. And this is the front part, which is talking about the minimal cost flow problem can be formulated as minimized total cost. And Cij is the transportation unit cost for sending down each units of flow on the arc ij. And there are two constraints. One constraint is so-called flow conservation constraint, and the first term of the flow conservation constraint is staying for no I, all the outflow. This part is the outflow, minus all the incoming flow, which is to no I. So ij, for summation of j, is from I to all the, summing up all the j to the outflow. And the second term is the inflow, which is from all the j coming into I, no I, equals to the node supply or demand. If the node supply is greater than 0, means this particular node is a supply node. If Bi is less than 0, and this particular node, we call that demand node, which is requires certain flow come in. If Bi is equal to 0, and this node we consider is a called transshipment node. Basically, whatever come in has to go out. That's the purpose. The second constraint is all the flow is positive. There's no negative flow. And the Python implementation start with using the Network X. Okay, input we're going to using the matplotlib. Okay, and we're going to using the Seaborn as part of a plotting problem. Also, we define some of the parameters used for all the plots in this notebook. Plot size is 20, plot width is 8, plot height is 5, and defining the figure size, the axis label size related to the figure size, and title size, and so on and so forth. Okay. So we're going to implement a node problem. So we're going to define, this is actually a node problem we're going to do today. Okay, a node problem. First we're going to define a graph, which is basically a digraph from that. Okay, define a digraph. Oh, sorry, I have to run this set first. So we're going to create a graph called digraph. It's a directional graph. And second, we're going to adding nodes to this graph. Adding node to this graph. For example, the node 1 is demand is -300. Here is asking for demand, so actually, the negative of the demand basically represent the supply. Here I'm going to have a color node for that. It could be a red if you want, or I have here using a hexagon code. Okay, so this is the node we have. I'm going to copy this. We have 3 nodes. I'm going to make it color the same. This is the second node. Also have a 300 units of supply. And the third supply node, which only have 100. Okay, and using the same color code. Then we're going to have a 2 transshipment node. Okay, I'm going to do the same. 2 transshipment node is node 4 and node 5. And demand and supply equals to 0. And color, we're going to give it another color, so you'll see that. For example, I'm going to copy this also, duplicate it to here. Then we're going to have 3 demand nodes. Oh, sorry. Copy that. Six, 7, and 8. So total we have 8 nodes. And this guy demand node 6 demands 200 and 200 and 300. So totals all together 700. So supply node actually match demand node. And I'm going to change this color. How's that? All right. I'm going to change that. I'm going to start adding edges. Okay. Ooh. Should be lowercase, adding edges. So 1 to 4, edges 1 to 4. The weight is 2. And capacity equals to, since we didn't deal with capacity in this particular example, so I'm going to call it 9999. Okay. So I'm going to add the rest just by copy and paste to my demo notebook. Okay, I'm adding all the edges to this node. There's edges from node 1 to node 5, and node 2 to node 4, and node 2 to node 5, and so on and so forth. So I'm going to run this. Sorry. Should have Okay. So we add this. I had some typo. I'm missing an equals sign over here for the color and missing an equal sign over here. After some correction, this is done with the graph. Next, we're going to plot with the network. First, we're going to give some node position, like we had it in the previous notebook. Okay, so this will define node. The node position for node 1 is 1, 3. The first one represents X, the second one represents Y, is in the coordinate 1, 3. Second node is 1, 2. Okay, and the third node is 1, 1. So the first three nodes is lined up in the left hand side. And node 4 and 5 is 2, which is X is in the middle, is 2, 2.5, and 1.5. So node 4 is higher than node 5 with 1 unit. Node 6, 7, and 8 is X coordinates on 3, which is the right hand side. And node 6 is on the 3, node 7 is on the 2, node 8 is on 1. And also, we're going to grab the NoColor from, we're going to grab the NoColor from the color properties. Okay, it's a list. We're going to get it from my graph. So next, get no attribute. Okay, from graph G, which is I want the color information, and I want its value. All right. Okay. So then we can start plotting this. Draw. We've done this before. Draw the graph of G and position equals to no position. No position, and with label, yes. I want the node number showed up inside the node. Equals to true. I want the node label, and then font color, I'm going to give it to red in this case. And node size equals to 800, I think. Yep. And let's do NoColor now. Equals to NoColor list I just defined. Okay. And also I'm going to, okay, let's do this, see if it works. Okay, showed up, and this is the example we had before. 3 supply node, 2 transshipment node, and 3 demand nodes. Okay. Now I'm going to label the weight. Weight is basically the cost. Okay. So I'm going to create a label 1 equals to, again, this time I'm going to get the edge information from the graph. Get edge attribute from G. I'm going to get the weight. Okay. And put it into label 1. Now I'm going to draw the label. I'm going to draw the edge labels using network X. Graph G. Again, is no position, so I can properly mark the node weight on here. So using the proper node and edge label equals to label 1. Okay. Finally, I want to show this graph. We've done this before. Sorry, typo again. Adding a S right here. Okay, works. So here is 1, 2, 3, 4, 5, and 6, 6, 7. Each one of them, the cost is listed on there. We're going to solve this problem using the network simplex. Let's do the capacity planning for capacity scaling first. Solving this, I'm going to using flow. Solving this, just simply call network X capacity scaling algorithm, and using network G, and demand equals to demand, and weight equals to weight, okay, portion. And there are two things can be returned from this capacity planning first. First is the flow cost. I'm going to call it flow cost and flow dictionary. Okay. So it's done. Let's see what is the flow cost for this. It's 1500 like before, and the flow dictionary. Okay. So here is from node 1 to node 4. Okay. The flow is 4. From node 1 to node 5, the flow is 296. And from node 2 to node 4 is 300. From node 2 to node 5 is 0. Okay. From node 3 to node 4 is 100. And from node 3 to node 5 is 0. So this second information represents the amount of flow on that pair of nodes. Okay, so on and so forth. So next we're going to compare the solution with the see if it works for network simplex method. So we're just going to copy this again. See if we can modify. I'm going to call this guy 2 and 2. And instead of capacity scaling, I'm going to call it network simplex. Network simplex method. Same thing. I'm going to using demand. Okay, capacity. Here I can actually put in capacity if I wanted to. And for this particular example, it didn't make too much sense. Okay, and I'm going to put in capacity as well. As well. Solve it. Let's do flow cost 2. Okay. Again, is 1500. Confirm with our. Let's look at the flow dictionary. 2. And you can notice that this algorithm, network simplex algorithm, give a slightly different solution, but with the same objective function value. For this, from node 1 to node 4, instead of 4, is 100. From node 1 to node 5, instead of 296, it is 200. And similar situation happens for node 4 and node 5 flowing into the destination node, the demand nodes. So for example, from node 4 to node 6 is 200. Again, from node 4 to node 7 is 0. However, from node 4 to node 8 is actually 300 instead of a 204. Same thing for node 5. For node 5 to node 8, in the previous successive shortest path algorithm is 96, and this one is 0. But I have exactly the same objective function. And simplex method, as we said it before, always find the extreme point. So instead of these fractional flows separate into two different transshipment nodes. I'm sorry. And if you look at the cost, and actually from node 1 to node 4, then to node 8, and from node 1 to node 5, then to node 8, they're actually the same cost. So from node 1 to node 4 is 2, from node 4 to node 8 is 1. So added together, each unit is 3. Same thing from node 1 to node 5 is 1 unit only. However, from node 5 to node 8 is 2 units. So there's another 3. So there's can have a multiple solution in this case. And this particular tutorial actually demonstrated for you. And this is two identical solution, okay, and we can figure it out. And I have one more example in the notebook I uploaded online, and you can try. And these things I show you two different methods. And the first part is fairly easy. Set up the graph, plotting the graph. We've done this before, so I just refresh your memory one more time. And solving this for the capacity scaling problem, which is the successive shortest path algorithm equivalent. Now I compare my result with the network simplex method. So with this, we show you one of those algorithms we talk about in the lecture. I'm going to conclude this lectures, and we're going to explain another algorithm called primal and dual algorithm for minimum cost flow problems in the next lecture video. I'll see you in the next lecture video. Bye bye.